South Africa had a blackout, and there was an article the other day published by News 24 saying, yes, it happened on the 5th of December 1975, and they quoted the Eskom heritage site as their source. So I challenged them and said, that's not the case. And I actually then said to them, the closest we got was a day earlier when there was a partial blackout after a Buzzone CT failed at a major Eskom transmission substation near Witbank, and that caused about 45% of the country to go dark for 5.5 hours. But that's the closest we've ever got in recent history. Before the 1975, there's not much history, documented history that we have, and Machiel can probably say a lot more about that this evening. But I'd also like to just remind you what happened in 2004, I think, when there was a major blackout in the USA, in New York area, that affected about 60 million people. Just after that, they asked the director of the Italian Transmission Authority whether that could happen in Italy, and he said definitely not. And they asked the same question to the Swedish transmission operator's chief officer, and he gave the same answer. And within 3 weeks, both countries had a blackout. So don't say never, but there's the possibility, and I hope Machiel will this evening take us through some of the pitfalls and the challenges that one can see. So a bit more about Machiel Viljoen, who's our speaker this evening. He obtained a BEng from Pretoria University, and then an MEng from Northwest University. He spent most of his professional career in Eskom. He represents South Africa on some of the SAIEE committees where he's provided some valuable contributions. He's been part of the committee that has written and rewritten the South African Grid Code, and he spends most of his day investigating multiple unit trips at various Eskom power stations. So whenever more than one unit trips at the same time, he and his team will go and investigate that. So I think he's very well qualified to talk on the subject because he studied it extensively. Machiel, we look forward to listening to you, and the floor is yours.
Mr. Kock, thanks for having invited me. It's a privilege and an honor to address members of the South African Institute on a topic that I've worked quite a bit on, and that is becoming, I think, more and more pertinent as time progresses, as you've indicated. I think, let me just find my mouse here and I can actually start the presentation. In one of the most simple abstractions of what a power system is, you can try and conceptualize a power system as being a set of distributed loads, customer loads, a set of distributed generating plants or generators, and some form of network connecting these and interconnecting these to one another. Very, very high level, that is a conceptualization of what a power system would represent. Now, if you accept that that is a conceptualization of a power system, then a blackout can essentially be conceptualized as breaking the link between the customers and the generators. And once you've achieved that, and on a large enough scale, then you've essentially achieved to black out a system or a part of a system, a region of it, or something along those lines. And that is essentially the level at which, the simplest level at which you can try and analyze this phenomena. I'm going to quickly unshare this just briefly, because I want to actually read to you a well-written event. And this is the USA event, the USA Blackout event that occurred on 13 July 1977 when New York City was blacked out. And city blackouts are particularly interesting because it happens fairly seldom, but if you've visited large European cities and US type cities, you realize that it's almost a category on its own. Normally these cities, or very often these cities, have got their own internal generation capacity, often in the form of gas type generation. Sometimes even other forms of it. Nowadays a lot of renewable penetration, rooftop applications, things like that. A lot of infeeds from a power system external to the city, and the city itself has many vulnerabilities. If you think, for example, of a metro system that goes without power all of a sudden, it's fine if you're on the metro station to a certain extent. You can probably walk those long escalators out if you want to. But if you're somewhere in one of the tunnels midway and the system blacks out, there's a ventilation problem, there's a heat problem, there's a danger in terms of evacuation problem, there's all kinds of things. You can say, but we're not really as affected by that doing load shedding in South Africa, but bear in mind that the critical infrastructure systems in South Africa doesn't get interrupted with load shedding. We deliberately try to not interrupt things like the Gauteng, for example, and things like essential water pumping and purification and so on. So it's not quite the same. In my estimation and my view is that this should be seen by SAIEE, city blackout should be seen by SAIEE and other bodies like that as a subset of these types of events and studied on their own merit. Now, this event that I'm quickly going to just read to you, it's not very long, don't worry. I encountered the first time in my third year in a third-year textbook entitled An Introduction to Electric Energy System Analysis. And that's where I found it, and it captured my imagination right from the start when I read this. This is on chapter 12 in the book, and it is entitled Emergency Operation. So it goes like this. 2200 hours. On this hot and muggy night, the city electrical load is peaking around 9,000 megawatts, about half of which is being imported via overhead tie lines and underground cables. The utility is operating in the normal state. An intense electrical storm is moving across the area. 2037 hours, a severe lightning bolt hits a transmission tower carrying two 345 kV lines, causing permanent tripping of both. The network loses a load carrying capacity of about 1,000 megawatts, which load is instantaneously shifting over to the remaining lines. The system is now in an alert state of operation. 2255 hours, the city generation has been raised by 550 megawatts to take the strain off the tie lines, all of which are still operating below their thermal limits. System still in an alert state. 2056 hours, a second lightning strike cripples a third 345 kV line. Within a fraction of a second, a fourth line trips due to the ensuing power transients. Remaining lines are now pushed over their thermal limits. The city load is being carried, but the system is now in an emergency state. Every serviceable generator in the city is running. Oh my goodness, I lost my spot there. Apologies for that. I wanted to just go down a bit. Incidentally, this is how you create tension. You interrupt yourself right in where the story is at a height. every serviceable generator is running 2119 hours due to a thermal expansion. The conductor of 345 kV line sagged deep enough to cause a short circuit via a small tree. The line trips, causing further overload of the few remaining ties, which now, one by one, break open. The system is now in an extremis state. 2129, the last tie with the outside world trip. The system now finds itself with a deficiency of 1,700 megawatts, resulting in rapid loss of frequency. Under-frequency relays automatically initiate preset load shedding of section upon section of the city. The loss of frequency cannot be halted, and the generators are tripped automatically and manually to avoid catastrophic machine damage. 2136 hours, New York City goes totally black. Now what you can see here is that a very important aspect and feature of a blackout is that a blackout doesn't just happen. You can't just switch on or switch off a switch and a blackout has occurred. A blackout is a sequence of discrete events taking place over time. And that's a very important aspect to remember when we look at this. Okay, let me go on. Okay. Now the US, if you look at the historic record, they've had their first wake-up call in terms of a large-scale blackout, which was the Northeast blackout, which occurred in 1965 already, and they impacted 30 million people at that event. Then in 1977, New York itself blacks out. That's the event that I just read to you. Then in 2003, Prof. de Kock just referred to it, 55 million people more or less impacted by another US Northeast blackout. And then in 2019, on a much smaller scale, the blackout Manhattan with 73,000 people being impacted. Now what you can deduce from this is that even in first world countries, trying to stop and prevent even recurrence is not that simple. You can imagine that after 30 million and 9 million and 55 million people have been impacted, all of which are voters and so on, they probably pulled all stops and tried to make every effort to try and stop the recurrence of this type of event. And they failed. This is what we all know to be true inherently, and that is entropy. You know, it will always be a function of time. It doesn't matter what machine man makes, what system man devises. It will ultimately be subject to deterioration and ultimate failure. You can try and manage it. There's much you can do, but to definitively say that something is impossible is not that simple at all. Here is the annual blackout, large blackout events. I looked at blackout events of over about 10 million people impacted in any year. And I just added, if there's more than one event in a single year, I added those events together to just give you an idea of per year what type of large-scale blackout events occur internationally. And you can see if you neglect the over 700 million people event, we often hit about between 100 and 200 million people somewhere in the world. That's not uncommon. And it doesn't, the frequency is not stopping, as you can see. It's just carrying on. There are international work groups. There are SAIEE work groups whose sole purpose is it to study these things, to share learning, to warn, to share best practice, etc., etc. We're not stemming this. This is getting ever more troublesome, I think, from an international point of view. And we all know this, but this is certainly proving it if you look at these type of numbers. Now, I've done a bit of work and a bit of analysis on the event that occurred, the Northeast blackout of 2003, to just show you that when we talk about blackouts, it's not so much the network that gets compromised. It can be the network that gets compromised, but very often this is not the case. Ironically enough, if you read events following blackouts and papers that get published internationally, they almost focus exclusively on the role of the network, the system, the grid, the defenses in the grid that has failed. And nobody ever seems to worry much about the generators. They'll mention the generators, so many generators have been lost and so on, but nobody would ever actually analyze that part of it. They'll go into extreme detail into, did the network protection operate correctly, as per design, was the communication fine, and the generator side is largely being neglected. So in this 2-hour window, this is the total event, from the start to the end. And the red lines are transmission assets that have been lost in the process, and the blue lines, I hope the color is more or less the same on the screen. Yeah, it is more or less. The blue lines are the generation assets that are lost. The scale on the left-hand side is logarithmic to allow for the vast differences between the peak where this event occurs and the normal running of it. So you can see that since the inception of the event, about an hour passes. An hour whereby things could have been remedied, maybe, action could have been taken, it's certainly a lot of warning. And then all of a sudden, something happens. And what happens is that the operators of the system fails to realize in the hour leading up to the event, to the main part of the event, that the system is slowly getting overloaded. And overloading, as we've seen in the previous discussion where I read the text to you, is a big part of the problem, because eventually the SAG, flashovers and things like that will take out lines. And unfortunately, as I said earlier, blackout is a sequence of discrete events. Unfortunately, the step size of a discrete event are often very large. If you lose a power line, there's a huge amount of power that was being transmitted over it, and that immediately needs to shift. So what I did in the next slide is I've taken the part where you see the mountain range in this slide, and I've unpacked that to just hone in on 2 minutes of this event. And it leads to this. Once again, the light, what is that, orange type color are network assets that get lost. The blue events are generation assets that are switched out. Now you may well ask, did the system operator not do anything in this time? Because, as I said, an hour is, in any language and even South African terms, it's a long time. You could have done something about it. They did this. The continuous line is load shedding. The scale is on the right-hand side for that. They shed 10,500 megawatts of load, and they did that early on. They did that in minute 25, more or less. They shed that. The green bars are transmission assets that get switched back in by the system operator. So they switch assets in, and as you can see on the left-hand side is the number. So at some point they're switching 16 lines back in or 16 assets back in, and they try and do things. So the system operator is not just laid back and waiting for things to happen. They were actually very active. They didn't save the event, and therein lies part of what we're looking at now. So let's just look at that event. The system frequency in North America is 60 hertz. The system frequency decayed with 1.54 hertz and overshot by 3.27 hertz. That's vast. That's enormous. The total loss in megawatts is 63,000 megawatts, 63 gigawatts of power they lost. They shed 10,500, 55 million people interrupted. Transmission lines lost 400. Other assets in transmission, 152, of which reactors, transformers and capacitors are among those. Generation losses, 531 units switched out at 261 power stations. Of those, 20 were nuclear reactors, there were coal units, there were liquid fuel units, and quite a bit of wind. Enormous. The scale is staggering. If you compare this to South African conditions, I mean, this is like just off the chart. Nonetheless, this is the nature of it. And on that bar chart of mine where I show the large events, this is not a large event. This is not, in international terms, that was just a normal run-of-the-mill type event. As I said, many events are over 100 gigawatt, 100 to 200 gigawatts. That's very common. This is 63. This is not a particularly large event. So how does a blackout work? Some facts that you need to understand is that certain things, there are inherent weaknesses in certain things. You can only, nature only allows you to do certain things, to ramp at a certain rate. That's, you can't do anything about it. So there's inherent weaknesses. Then there's often scene setup. In other words, a part of equipment, a piece of equipment fails and doesn't get replaced in time. So afterwards, when you analyze the event, you realize that had that asset actually been there as it was designed, everything could have gone very differently. But we actually set the stage for something to happen. And then eventually there's a trigger. Something sets it all in motion, the first domino to fall. As I said, it's discrete steps. Generation and network assets get compromised. There are unique cases where it's only one of the two, but in most cases it's a combination of these two. And ultimately it's the disconnection that we're worried about. Now let's just look quickly to recap, and let's just look at the South African historic record. If you look at that, now, a bit of history here, and I deal with it somewhat later on in the presentation, but is that the interconnected power system in South Africa gets finished in 1973. So in 1971, they've interconnected, we, Eskom has interconnected the Gauteng region and Mpumalanga region as we would know it today to Natal, and there were two power lines going down there. And in 1971, we lose both those lines, and we black out Natal, and the newspapers at the time said it's the worst interruption Durban has ever had. And they were blaming the Eskom reality on it and said that when they were running it, this never happened. So, okay, there's definitely that. But then in 1975, just a year or two after the national grid was established, we had three network cascading events, one of the ones that Prof. Kock just mentioned, and in 1977, two more. The worst event is the one that was referred to. It's a Vulcan substation CT failure that started it all. 24 units at the time tripped at 4 power stations. The network frequency 47.5 to 52.5. I very much suspect that the instrumentation went saturated. It's just too coincidental for things to saturate at exactly 0.5. I don't buy that. So I think it was worse. This is what was recorded. It was at least that. It was probably worse. The second worst event we've ever had in South Africa lost 24% of the national load. That was the second most serious event South Africa has had. That was an event where 2 units at Koeberg tripped along with 2 units at Letabo within half an hour or something like that. So if you express it in absolute terms, that was the second worst event. It wasn't the second worst event from a timing point of view. If you have such a large separation between the first and the last events, obviously the effect on system frequency isn't that pronounced. But nonetheless, it was the second worst one was a 24% one. So the question that one really has to ask is, if you think about likelihoods of blackouts, what is the indicator that you should really be looking at? There's a lot of unit trips, there's a lot of load shedding. Is load shedding the right metric to look at to tell you how close we are? That's probably the imminent question. Let me recap South African history for a bit, because it will give you an idea of how the generation as we know it today, how that works. 3 factors basically coincided more or less in history for us to be one of the first adopters of large-scale electricity. One was the discovery of precious metals, diamonds and gold. Second was the commercialization, right about at that time, of commercial electric things by Edison and Westinghouse. And thirdly was, shortly after the discovery of precious metals, is the discovery of coal, which in the absence of that would probably not have resulted in. But that together culminates in early uptake in South Africa of electricity. So if you look at it, and you look at that little graph, if you've ever visited Gold Reef City, that is a stone crusher that is standing there at the gate, very impressive, huge. You can see people there in the left bottom corner to give you an idea of scale. And this thing had like a crankshaft there in the middle, and it stamped down on the rock at the bottom and crushed that into fine powder or fine and finer material. And those two wheels on the side were the driving the driving points of this machine. So you needed steam machinery, things like this one, where a belt would go over that large vertical wheel there, from the one on the one side with a belt to the one side of the crusher, and on the other side the same thing. And you could run two of these machines on either side if you wanted to. And that was the reality very much. That was the energy that we had. And then eventually the adoption of electricity, obviously, to try and replace all of that. Interesting little extract that I found in the Eskom yearbook, the very first Eskom yearbook, not 2023, 1923. As I said at the bottom. Two large companies, this is talking about the SAIEE region. Two large companies, several small private companies, and many claim holders working in a small way are operating in the district. Not only are the normal mining operations seriously restricted in the dry season, but further development cannot be proceeded with any degree of confidence owing to the shortage of power. Then they talk about a private generator, and it says, this plant has been supplemented from time to time by various small steam and water plants, and some of the mines are hoisting with animal power. But the total power available is inadequate to meet the requirements of the mines in the district. So you can see, even from the very first yearbook, there was a need to develop very rapidly. And that is exactly what happened. So let's quickly look at how it developed in South Africa. Initially, only at growth points. So you had mines, you had towns, and there was some local generation. In this period of time, there was local networks, and this is the time when we had Generation 1 and Generation 2 type generation plants. We had a third generation plant coming online more or less in 1923, when the regional undertakings started in Eskom, and Eskom started assimilating plants that were constructed often by other people and plants that they built themselves to start operating these. And there was also some of the power stations generated compressed air, mainly for mining purposes, and that was part of it. That was eventually stopped by Eskom in 1960. In 1905, Robert Hammond in the IEE, which is part of our legacy here today, wrote a paper entitled Electrical Power Distribution on the Rand. And there he advocates for large central power stations, arguing essentially that larger power stations are just more economical, and you can use the economy of scales and leverage your buying power and optimize power generation from that point of view. And then we get the fourth and the fifth generation power stations coming online, and they started seeing the light in the grid context. So that's where I want to focus on. So if you talk about first generation power stations, the things we had at Kimberley and so on, power station where the total capacity is less than 5 megawatts. It's one-on-one applications. In other words, you've got one mine, you've got one generator, there's a piece of wire in between. It provides you with the power you need. Private ownership, dedicated networks. Second generation power stations uses compressed air, power station capacity less than 50 megawatts. They use generating sets And the generating set is basically a turbine and a generator combined. They had far more boilers. The ratio between sets and boilers were 1:4. In other words, very important to understand is that much of your maintenance capacity sat in the boiler design. They knew boilers were far less reliable than generating sets, so you had many boilers. And while one has broken down on a tube leak, they're repairing that and they're using another in a common steam range, and the power station can just keep on going. Thermal efficiency in those days, between 16 and 18%. And every single power station had black start capability, of course, because if you are a single power station in a network and you lose your few machines online, then you need to black start. It's that simple. So in this case, we have a single power station or single plant supplying many customers, but it's one to many or one to several, let's say. Third generation power stations, this is in the period just before national grid formation. And here you again have a condition where you had more boilers than sets. 20 to 23% thermal efficiency, and here you have it, you've got local networks. In other words, there's a local network, let's say a Western Cape undertaking. It's got a few power stations in it and you've got a few customers. So now there's synchronous operation taking place between power stations. Power station capacity not exceeding 500 megawatts at this point. Now this is Eskom book that I took the central page from. It's 1975 book that I took it from, and there you can see what the regions looked like, or the undertakings at that point in time. So the yellow one was called Transvaal and Orange Free State. The one, the bottom here was Western Cape. You've got Border, you've got Natal undertaking, and so on, North Cape and so on. So you've had these undertakings, each of them essentially being independent. And in the next generation, Eskom embarks on a project within 4 years to connect all of this together and making a single grid. And in that we get the fourth generation power station. Fourth generation power station abandons now the idea of generating sets. It goes now for generating units. And now there's a one-on-one mapping. You've got one boiler, and that boiler supplies one specific turbo generator, and that's a unit. Power station size limited to not more than 2,500 megawatt capacity for the station. It doesn't have black start capability, and the thermal efficiency now ranges between 25 and 28%. So what you now need to understand is that where at first the maintenance capability was actually provided for at power stations, now it is assumed it exists somewhere in the network. It's not necessarily at your power station. If your unit goes down, the reserve is possibly sitting at another power station. And then ultimately we get the fifth generation power stations. That is Tutuko, if you're wondering. Here we've got 50% operation. In other words, the units now have been further diversified. A unit can run at half load, which wasn't possible in the previous configuration. So now the units are fully mature as we have them today. The units, the stations have no black start capability. They're never more than 5,000 megawatts for a single station. Thermal efficiency can be very high with supercritical technologies. But they've got islanding capability. In other words, the unit can back down from the grid and can supply its own auxiliaries, and that makes restoration far simpler and easier. But what are we really worried about? Units will always trip. Things will break down. Your car, when you go home, might break down. This happens. These are machines. They can break. So looking at a single unit trip, or even the incidence rate of single unit trips, is not a very effective measure. What we're really worried about for generation failures to culminate in a precursor to a blackout is when these things start happening in cascade, when one unit is not just acting by itself, but it is pulling other units along down with it. That is the danger. There are two concepts here. The one is a multiple unit trip, when more than one unit trips directly from the same cause, and the second one is a multiple unit disruption. That is more the type of thing when you have, let's say, you encounter ambient temperature problems and all your units need to go down, or there's a lot of rainfall in the country and everything is affected. It's not specifically trips, but everything gets derated and the output gets reduced. The South African grid code is the only grid code in the world that has got a significant section on this area, this space, the multiple unit trip space. No other code in the world has got this. And it talks about how you should operate, maintain, and design your plants, so that the risk is to a certain amount contained. So this is something, a feature that we've got that doesn't exist elsewhere. Here and there, one of the European places have started to copy a bit of it, but very, very superficially so far. If you consider a power station, this is the picture that you come up with. There's a primary energy source. It gets converted, but it gets converted in a common plant, a plant that is not dedicated to a specific unit. And there are many common plants in a power station, and they share their services amongst the various units. Then you have the units, and unfortunately, as much as we try to unitize them so that they're entirely independent of one another, there are some features, some functions that they do share amongst each other. Think, for example, something like earthing. You can't have an earthing of Unit 1 and an earthing of Unit 2. It's one earth mat. When you go to extremes like Koberg designs, if you go to nuclear type designs, they've got a more aggressive approach to unitization, and these little horizontal arrows become really, really very small, and there's very few systems that get shared amongst units. But they still have common systems, and if you think of the Koberg design, there's still one intake, 1.1, let's say ocean temperature, for example, that would affect both units. So it's basically impossible to entirely divorce any design from its surroundings. And then, of course, there's a power system sitting on the outside, and that should not be underestimated. The power system, very often, is the very mechanism through, or the very, let's say, corridor through which disruption comes into the plant. And you can't avoid that. As much as you can try and unitize plants and systems, you can't avoid that. Everything needs to supply into the power system ultimately. So there's a pyramid, a disruption hierarchy that we implement at all power stations nowadays, modern power stations. At the very foundation of it, it's called fault tolerance. In other words, you try and design the plant to be as resilient as possible. It should not fall over if the voltage goes out a bit of its band, when the frequency goes out a bit. The second brick in this pyramid, the second layer, has to do with redundancy. In other words, you try and make it such that if a specific component in a system fails, there's another component that you can pull into service and it doesn't affect your output at all. Thirdly, there is subdivision. Subdivision has to do with, if you think of a modern power plant, let's say a coal plant, then you've got two draft groups, a left-hand and a right-hand draft group. If the left-hand draft group goes down, the unit can still continue at half load using the right-hand draft group. So the system can be subdivided. Then there's state transitioning, going very closely with the previous one, where the unit can recognize specific disruption conditions and assume new pre-calculated load points, knowing that it will be stable at that load settling point. Then there's process isolation. Process isolation has to do with, you can shut down a specific process at the plant while other processes still remain in service and continue to operate. Good example would be at a coal power station where you can trip the turbine, but the boiler would remain on load. If there's not, let's say the cause wasn't in the boiler area, there's no point in shutting the boiler down unless you didn't have this capability. But otherwise, keep it on load, it will enhance return to service. Energized tripping, islanding capability. It's a capability where you step down the entire unit, lock, stock and barrel from the grid. You separate from the grid so that all nonsense and disturbance that happens on the grid doesn't affect you any further. But it is technically complicated and risky to do, and it's not simple to do. You need very good control systems and so on. So in the Eskom context, all the later power stations after Matla features this function, even Koeberg. And then as the very last resort, if you've got no other option in the case, then you can de-energize strip. In other words, you shut down, everything is dead, the lights go out, you fall back on batteries and diesel generators. That's the last step if you can't avoid it. The restoration model we've got, I don't want to spend too much time on it, let's say the blackout and restoration model we've got, is essentially a model whereby we say that there's always disturbances on the left-hand side. Sorry, I suppose that's a bit small. It's such a busy little slide. There are always disturbances on the left-hand side. Now and then one of these disturbances will breach your barrier that you've got. Your resilience barrier will be breached. If it breaches, you try for it not to activate a common mode type failure. So if it breaches, it should just shut itself down. It shouldn't start a cascade. But now and then, a cascade event would be initiated, and now dominoes start to fall. And then you've got a cascade containment barrier, a barrier that is aimed and designed and maintained to stop such a cascade from circling out and escalating too far. However, if it breaches, you have a blackout. And then you've got units that are sitting there, and you try, and then you go to the green part of the system on the right, and the green part is where you try and restore. Unfortunately, there's a natural barrier there, and that barrier is aimed, that you can call it Murphy's Law, you can call it reality, you can call it physics. Things start acting against you. You've only got so much fuel you've only got so much water in your dam. Once it runs out, you're dead. So there's another barrier, the red one, that tries to stop you. So our framework that we're working on is something like this, where we've got frameworks for each one of these sets, and we've got a monitoring layer on top of that. So the management framework that we use presently is this, is whenever such an event, a multiple cascade event does occur, there's an independent investigation using subject matter experts. They aim to find the root cause. They action specific activities to avoid recurrence. They share their learning, and within the context that we find ourselves in, they use inputs also from the Southern African power pool and not just the South African system. Now you may ask, what causes or trigger these things? Here's a list that I made. This is by no means comprehensive. These are typical things, natural things, weather, earthquakes, flooding, solar activity. Canada has blacked out their system twice due to solar activity. Network disturbances, there's a whole host of them that you can think of. I'm not going to go through it all. These plant problems that you can get, a plant that breaks down, common mode failures, obsolescence, risk acceptance, which is, I think, becoming too big at the moment. Then there are human things. People are often the cause. Errors have been very, very often the cause. A guy walks to the wrong unit to isolate something and sets the dominoes in action. Then there are design mistakes you can make. You can design a single point of failure type system. Silly, but amazingly, when we investigate it, we often find this. Despite the fact that engineers know to avoid this, sometimes it's overlooked, and despite the fact that designs have been reviewed and vetted and everything, it's overlooked. Redundancy, disrepair and upkeep, big one at the moment. Obsolescence, always an issue. Oh, I've duplicated obsolescence, sorry for that. And then there are other things. Legislation, for example. The moment we're suffering from very, very tough environmental legislation that prevents full operation of many units under many circumstances because of the pollution levels. There are several examples that we can use. The product life cycle, a very big one, is that nowadays with the digital type systems, things don't last very long. You know, you would put in a new control system, and the OEM would tell you from the get-go, you know, you've got 15 years if you're in the beginning of the product cycle, and then you should have replaced it already. Emerging risks. So what do we see on the horizon? What's threatening us? Everything works on networks nowadays. That's a big risk. We found various examples where the network itself was the problem to communicate the, let's say, the problem from one plant to another, from one system to another, something like that. Distributed intelligence, you set up intelligent devices in various locations. A very good example is where we, a few years ago, tripped the entire SAIEE wind farm out. Now, SAIEE consists of, let's say, just less than 50 wind turbines, each one of them entirely separate. How do you trip that? You trip that by miscalculating a setting and applying it to every single windmill. Then, if you wait for the frequency to occur, and it's at exactly that point, then all of them see the exact same thing, and your commonality was actually a design, was actually the human thought, and not so much the failure of something as it is a human failure. The experience profile is a huge, huge problem in Eskom, but when I talk to my colleagues in other areas of engineering, this is not just a South African problem. OEMs agree on it. The skill isn't there anymore. The people are moving on, driven in part by the very short life cycle, product life cycles that are out there. That is part of the problem, but there are also other issues. Repairability of digital products. Old products we kept alive. We bought electronic components, you had a soldering iron, an oscilloscope, a drawing, you repaired them. You can't repair these modern things. They're multi-layer PC boards. They're impossible to repair. Cybersecurity is becoming a big issue, and every year or so I read about new events somewhere in the world where somebody's hacked something. Somebody's recently hacked the Chernobyl monitoring station. Can you believe that? It's not particularly dangerous, but I think they just try to prove the point that they can get into it and you know, upset things in that regard. And then renewable penetration levels is always a big risk, because if you really think about a renewable system, it is always highly affected by common climate type things. They are automatically in a specific zone, a specific region, where a thunderstorm or cloud cover would affect them in mass. Wind is a phenomenon like that. So the more renewables you've got, the larger your reserve margins need to be, and the more machines you need, dispatchable machines you need on standby to supplement when they come online. Now here is every single multiple unit trip event that has ever been recorded in Southern Africa. On the left-hand side, you see the megawatts. It's years at the bottom. Now, a single modern unit, just to calibrate you for a moment, a single modern unit, 600 to 800 megawatts. So that is about the 1,000 megawatt line. All the events happening below that are actually, it's multiple events, but the units were maybe operating at half load or something in the middle of the night. So collectively, they didn't represent actually so much. And then it goes up higher and higher. And the real dangerous events that we're worrying about are the really high events, of course. Now, interestingly enough, if you look at this graph, and this is the metric that I would propose is the best possible indicator that you can use to try and say to yourself, to try and say and get an idea of how likely it would be for events as they occur in South Africa, or Southern Africa rather, to actually compromise your system. Because this is not looking at individual events. This is looking at every event where units are working together, where they are cascading together against you. There's only 3 events that's been recorded that is over 3,500 megawatts. That's basically a single large power station you're talking about. The one on the very, very left-hand side is the one which we spoke earlier about. That was a 45% loss that occurred round about there. And then there are 2 others that's in that. But you can clearly see from this graph that the really big events are not really increasing. And that tells you about how the system is designed and maintained from a point of view that things act collectively together. Now, it is possible that the stars align tonight and something horrible happens. Of course it's possible. But from a predictive point of view, it is certainly not very likely. The next slide, I've now taken one further step on this. And what I've done in the next slide, I've identified, you can't determine from this slide what has just been a single power station that participated in the event, or which one of these dots represent multiple power stations. So the next slide does exactly that. The yellow diamonds are where there was more than one power station involved. And the star-like asterisk thingies, also yellow, are where the more than one power station was involved, and they were across border. In other words, where a South African power plant participated in a multiple unit trip with a power plant sitting in another country in the Southern African power pool. So that is the graph, that is the picture that you get from there. And as you can see, obviously as expected, the really big ones, more than one power station need to participate to bring that into effect. That's fairly obvious. But you can also see that sometimes there's more than one power station participating, and their combined effort or combined effect is not quite as high as you would think. So are there any good news in this little tragedy? Yeah, there are. I've written more than one paper on actually saying how lucky we are to have these problems. If you think about any system that we design, any defensive strategy, how do you test it? How can you possibly test something like how high the voltage would go? Well, you can, if you buy a new AVR and you put it in a generator, you can inject a signal and you can measure something and you can get an idea. But if you've got, for example, a contingency plan, how do you test that? And the other thing is, if you tell someone you're going to test it, they're going to prep for the test. Yeah, of course, who wouldn't? You know it's coming, so you would. So it's not particularly, although we base much of the assurance in our business on testing, it always eludes me in terms of how ridiculous the thinking is. The opportunity is really to use what is coming out here automatically without being set up, unprepared, analyzing it, and see how well your contingency plan has actually performed. Did people follow the procedure? To optimize and fine-tune your dynamic systems and your defensive strategies if you set up new protection schemes. Some protection schemes are highly complex. Talk about out of step between the north and the south of the country. They're not simple to test. This gives you that opportunity to do that. It can verify that you comply to regulation. It can establish for you certain assurance levels that otherwise would just be a type of a guess. Now you can say, we've seen it. And therein lies a lot of benefit. There's a concept of anti-fragile design. What that means is that you should try and not just correct what was wrong when the previous event took place, but actually to improve your design so that the next time that same set of circumstances will not take you out again. So you widen your envelopes, you add to your defense in depth, you adopt new strategies, whatever the case may be. And then lastly, it's very difficult to say how good South Africa is faring because nobody else is trying to do this. So if you would apply this from a benchmarking type of point of view or a tracking point of view, you could start sharing information. You can say how good or bad you are with regard to other people. And that's certainly an opportunity. Ladies and gentlemen, that's my last slide. Thank you very much for your attention. If there are any questions, I'd gladly try and answer them. Thank you, Prof.